treat today, and maybe you'll all wish you had brought some of your kids and family members to this talk. We have with us a colleague from just around the Beltway, Bruce Molnia, is going to talk about baked Alaska and changing climate, changing landscapes. I first heard about Bruce and his work in an article in the Smithsonian Magazine back in August, which was also called Baked Alaska, to catch your attention. And it talked about some of the research he's been doing over the last 30 or so years in Alaska, and it was augmented by a number of the photographs he's taken, this being one of them, the one that you see up on the screen right now, which is a comparison of, I believe, of the Muir Glacier between 1941 and 2004. So we invited him to give a talk, and he graciously accepted, and so here he is today. But occasionally, we hit these things. This wasn't by any sort of planning. Carrie Presser's going to put up another view graph right now for you to look at. This is Time Magazine this week. They must have known we made this invitation. Be worried, it says. Be very worried. If you can't read the rest of it, it says climate change isn't some vague future problem. It's already damaging the planet at an alarming pace. And I love that graphic as well. It's a lonely polar bear wondering where he's going to go next. A colleague of mine has been to Alaska recently, and she told me about her experience there when she was on a tour of the glacier. The tourist person said, you know, when you stand here, as they were standing someplace nearby, she said, this is where the glacier was in 1980. Of course, the glacier was off the distance. So then they walked a bit, and then the guide said, this is where the glacier was in 1985. And so they continued to walk towards the glacier. And the impressive thing about it was that the glacier was still a long way off. And that was when my colleague said that she realized for the first time that, you know, these are effects that you really see in real time. Bruce is a research geologist, or as he likes to call himself, a glacial geologist at the USGS, the U.S. Geological Survey in Reston, Virginia. He's also been located in Menlo Park during his career, but basically has spent 30 to 35 years with the USGS. He has a bachelor's degree in geology from Harper College, now the State University of New York in Binghamton. He was a pre-med major, interestingly enough, in college until he got a summer job with Columbia University on a research icebreaker in the Antarctic. How would you like that for a summer job? Well, most of us would. In fact, it impressed him so much when he went back to college, he said, I think I want to be a geologist. So he got his bachelor's in geology. He then went on to get a master's degree from Duke University in marine geology and a PhD also in marine geology at the University of South Carolina. Bruce has authored more than 200 articles. Oftentimes the articles consist of maps, and he's authored or edited several books as well, one of the more popular ones being The Glaciers of Alaska. Another book was Glacial Marine Sedimentation. He's also authored the Alaska chapter of the Satellite Image Atlas of the Glaciers of the World. And I think maybe you'll see some photographs from that atlas in the talk today. He is also the forum editor of GSA Today, which is the newspaper of the Geological Society of America. And in that capacity, he's authored more than 100 monthly columns on various issues affecting geology, but in particular glaciers. He's done research for 35 years and has been on field expeditions in all sorts of climates, equatorial, temperate, subpolar, and polar regions. But the focus of his research has, for the most part, been Alaska, and it really is a love of Alaska that has motivated much of this research. He has other positions simultaneous with his position at USGS. He's an adjunct professor at Duke University in the School of the Environment. He's been is a research associate at the University of Idaho, where he's been working on the Juneau Icefield Research Project. He's been, I think significantly, also a senior legislative fellow for Congressman Kurt Weldon of Pennsylvania. He did this on detail from USGS for almost 4 years, from about 2000 to 2004. And as part of that assignment, he was responsible for developing and organizing, coordinating the Oceans Caucus, which he tells me still exists. And it was a group of people, congressmen, who were really interested in legislation affecting oceans. While at USGS, he's also been acting chief of international programs, and he has spent 2 years also as the senior program officer of the NRC, Academy of Science, Board on Polar Research. Would you join me in welcoming Bruce Molnia?
Thank you very much. As you can see, my title is Baked Alaska, Changing Climate, Changing Landscapes. And as soon as I get the buttons organized here, what we're going to do for the next hour is take what will, I hope, not be too much of a whirlwind tour, but a very rapid look at the last 20 or so thousand years of climate and glaciers on Earth, what glaciers are, a little bit about current climate change, global climate change, regional climate change as it affects Alaska. Then we'll look at the question, what's happening specifically in a region-by-region basis throughout Alaska? Is Alaska baking? And then we'll focus into Glacier Bay National Park, one of the areas that I've spent quite a number of years working. And in the last decade, my focus there has been on reoccupying locations where photographs had been made anywhere as early as the 1880s. And going back, finding the same location, which in many cases, in fact, in almost all cases, we have no information on the old photos as to where they're from. It's a matter of recognizing landscapes, going back and saying this is where that picture was taken, and then taking a new shot and then doing both a qualitative and a quantitative assessment of the changes between images. So I hope we'll make it in the hour, but we'll certainly have a lot of fun trying. I'm probably the only earth scientist in the room, and so I don't want to insult your intelligence, but I want to talk to you about what we refer to quite commonly as the Earth system. And we talk about the Earth being different from almost every other body in our solar system because it consists not only of a lithosphere, but it has an atmosphere, a biosphere, a hydrosphere, and a cryosphere. And the common ingredient, the common entity in all of these is water. And water is also the reason we have glaciers, and it's the reason we have climate change. The hydrologic cycle and the climate cycles are directly based on water. And what we're going to do is look at where water on Earth is and see how important glaciers are in terms of this total water volume. The parts of the Earth system that we're going to deal with are this glacier-ocean coupling in here and the changes in land features, vegetation, and heat budget due to both climate change and changes in snow and ice. And so if I had several more hours, we could talk about a large number of other interactions, but that's time for another interaction between us. Let's focus in on glaciers and climate change. 97.2% of the Earth is salt water. Everybody knows that. The oceans are the biggest reservoir of water on Earth. The other 2.8% of water on Earth is fresh water. 3/4 of that is glacier. And so glaciers are the second largest reservoir of water on Earth and the largest reservoir of fresh water. I'll throw in a couple of simple analogies, but if there were 1,000 drops of water on Earth, 972 would be in the inland seas, 21 would be in glaciers, 6 in groundwater and soil moisture, less than 1 in the atmosphere, less than 1 in lakes and rivers, and less than 1 in all living plants and animals. And so as glaciers melt, where do you think this water goes? Goes into the ocean system, and it disappears from the other 7% of the Earth's water. So as glaciers change, the amount of potable and irrigation water also changes dramatically. And as population increases, there's going to be a far smaller quantity of water available for handling the needs of growing Earth populations. Now, other things about water that are interesting. Water, as it freezes, forms hexagonal crystals. And the crystals have all of the properties of a mineral. Glacier ice is a mineral, definite physical and chemical properties. Among these is the fact that glacier ice, which has a density of 0.917, is about 8% less dense than fresh water and significantly less dense than salt water. So when glacier ice enters the ocean, it floats. And also, as you'll see, as glaciers are thinning and lose contact with their beds because of their buoyancy, many glaciers are rapidly breaking up and falling apart. And the same is true of the ice shelves in Antarctica. And this is a function of the density of the ice, as well as the temperature change. But when you remove that ice from the Antarctic, not only, it doesn't have a major impact on sea level because it's already sitting in the ocean, but it has a major impact on the flow rate of the ice coming off the continent. And one of the biggest things that we're concerned about isn't the increasing rate of melting of glaciers, which is significant. It's the increasing rate of glacier flow into the oceans, from land into the oceans without melting. This flow of ice, the calving of icebergs, where there's a direct transfer of larger volumes of water from the land into the ocean than anything that we're looking at through melting. Now, a glacier, simple definition, perennial accumulation of ice, snow, rock, sediment, and liquid water. Liquid water is important. There are two kinds of glaciers that we talk about. We talk about polar glaciers, which are such as the glaciers in central Greenland and the Antarctic. At the South Pole, you've got 3,000 meters of glacier ice. Mean annual temperature, minus 40 degrees. You can do anything to Earth temperature, and it'll still be 10 or 15 degrees below the melting point and showing no impact of changing climate. Temperate glaciers like these two, mean annual temperature of the ice, about 0.05 degrees C. So a small amount of temperature change has a dramatic impact on both the amount of fresh water in contact with this temperate frozen ice and on the rate of melting. Small amount of climate change impacts this temperate glacier ice dramatically. And it's this temperate glacier ice that had been our biggest focus, because if you melt all the temperate glaciers on Earth, as you'll see, you can contribute up to about 1/3 of a meter of sea level rise. If you melt all the polar ice, you're looking at close to 80 meters of sea level change. So, 0.9, excuse me a second, did I miss one? No, okay. 0.7% of the Earth's ice is in temperate areas. And by temperate, we mean areas where the mean annual temperature is within a fraction of a degree of the melting point. And so glaciers in all 7 of these areas, 6 continents, North America, Asia, Europe, South America, and Africa, are melting. In fact, we'll lose almost all the ice in Africa probably within the next 50 years. New Zealand's glaciers are growing. In fact, I spent 2 weeks in New Zealand a month and a half ago, and I was surprised to learn that there's a significant increase in glacier growth at higher elevations in New Zealand, because as it's been warming there, there's been increased precipitation at higher elevations. And the glaciers on Mount Cook, the highest mountain in the country, have been thickening and have been studied for a number of years, as are some of the adjacent glaciers thickening. In Irian Jaya, we're losing all the glacier ice, and in fact, it may be a matter of just a few years before it's completely gone. So, going back to that 1,000 drop or crystal analogy, if you look at all the glacier ice on Earth, 91.4% is in Antarctica, 7.9% or 79 drops are in Greenland, approximately 4 are in North America, with 1 of those being in Alaska, about 2 are in Asia, and less than 1 in all of the other glacier-covered areas on Earth. Now, it's this 7 drops here that are the temperate ice on Earth. It's this 93%, these 930 drops, I'm sorry, 970 drops that are the remaining polar ice that will have minimal changes because of melting, but dramatic changes perhaps because of drawdown. So, as I've mentioned, a small change in temperature can have a dramatic impact on temperate glaciers. And when we talk about temperate glaciers, in some of the photos you'll see, don't be surprised that you see liquid water on the ice, in the ice, and under the ice. Glaciers are quite fractured, they're quite broken, they're quite porous, they're conduit systems, there are streams both in, on, and under, and water moves freely through glaciers. Now, one of the things that we're seeing in Greenland, and that's what this article in Time magazine and a number of other, in fact, this week's cover article in Science magazine are focusing on, an increase in the velocity of glacier outlet glaciers, the increase in the velocity of glacier ice in Greenland. And what you're looking at there is probably directly related to the fact that more meltwater is lubricating the bed of the glacier, reducing the frictional forces that normally restrain glacier flow, and contributing to up to a 1/2 an order of magnitude increase in velocity. And so those are the kinds of things that we're now talking about when we talk about the impacts of changing climate on glaciers. Not only is melting an issue, but we're now concerned about a number of other types of changes in flow dynamics that may even have more dramatic impacts on the interaction between glaciers and sea level. Now, Alaska, even though it's less than 1 drop out of the 4 in North America, has over 75,000 square kilometers of glacier cover. The largest glaciers, the Bering and the Malaspina, each are about 5,000 square kilometers. Now, that may be meaningless numbers to you, but if you were to take a map of the Bering Glacier and superimpose it on the same scale map of the east coast of North America, the Bering Glacier would go from Philadelphia to the White House lawn. It's that long. It's 140 miles long. There's enough ice in the Bering Glacier to cover the state of Maryland, probably to a depth of about 30 feet. These are insignificant glaciers in terms of comparison with the polar regions, but they're huge volumes of ice. In fact, one of my calculations is that there's about 45,000 cubic kilometers of water tied up in the glacier ice in Alaska. And what does it amount to? If you were to melt it, it would amount to less than a centimeter of sea level rise. So again, it's a substantial number, but it's really insignificant when you start talking about the polar regions. Now, how important are the glaciers of Alaska? Here are a group of comparisons that you can make between Alaska and all the other glacier-covered areas of Earth. You know, there are about 1,000 times less glacier ice in Africa, about 100 times less glacier ice in the rest of the US compared to Alaska. And you can see the numbers. Canada has far more ice. It's mostly in the Canadian Arctic and northeastern Canada. Alaska is about half the glacier ice of Asia. Here's a photo I took last summer, and what you'll see are a number of pictures that I try to put in the context of trying to explain changing climate, but this is the surface of the Mendenhall Glacier. And this is a picture in August, and there's several things that strike me, one being, you know, here's the glacier ice surface, there's no snow on it. The previous year's snowfall and probably a number of years of past ice accumulation had already melted away by this time when we're still in the melt season. And the fact that there's almost a 40-meter high waterfall in the middle of the glacier is a very unusual sight to see. But this is not unusual any longer in the temperate glaciers of the world. We're seeing more and more evidence of melting, especially in Alaska. And why do we see that? Well, here is a temperature record. This is departure from, here's 0, from mean annual temperature. You can read the dates, 1945. The record starts in 1947. By 1947, there are 21 instrumented weather stations in Alaska. And so here we're looking at temperature change. And here you can see degrees C. And notice, you know, temperature actually looked like it was decreasing through the 1970s. And then we had a major shift in the Pacific Decadal Oscillation. We had a major shift with the maritime fronts moving inland. So we're getting more maritime as opposed to continental climates throughout southern Alaska. And this has had a major impact with a 2 degrees C temperature increase over the last 30 plus years. However, as you'll see when we look at some of the other evidence, Alaska has been warming for the last 250 years. And in many places, glaciers in Alaska have retreated or began retreating as early as the mid-1700s. Now, let's talk about the current observations of glaciers in the context of the last several thousand years, or in fact, in this case, the last 20,000 years. 20,000 years ago, most of the northern part of North America was covered by continental glacier ice. New York City had a mile of ice on it. So did Chicago. So did Pittsburgh. So did Seattle. So did Minneapolis. That ice began to melt. Well, let me back up. Even before that ice melted, you had 8% of the land surface, 8% of Earth's surface covered by glaciers, about a quarter of all of the land surface, and about a third of Alaska. And during this last glacial maximum, sea level was down more than 100 meters. If you were standing on the Maryland shore today and were looking out beyond the horizon, you still would not be able to see where the shoreline was. Shoreline was about 100 kilometers further east today than it is today. And global sea level rose beginning about 15,000 years ago and by about 6,000 years ago. So it took about 9,000 years for it to come up over 100 meters. It stabilized at a level not too much different from today. And since then, it's fluctuated significantly. And so today, when you compare those numbers, about 3.1% of the Earth's surface is covered by glacier ice, as opposed to 8% during the last glacial maximum. Remember, it was 25% of the Earth's land surface. Now it's about 10.7%. And it was about a third of Alaska, now it's only about 5%. So there's been a dramatic disappearance of glaciers over the last 15,000 years. And that's not the first time it's happened. When you look at the geologic record, we can find at least 100 comparable events over the last 2 billion years. So glaciers come and glaciers go. Glaciers will come and go as long as there's a climate, as long as there's an atmosphere, and as long as there's an ocean. However, during all of these past events, no one lived in the coastal areas. And no one was dependent on resources such as water to provide their existence. That's the only real difference. We may be changing climate, or we may be accelerating the rate of climate change, but this is not the first time climate has ever changed. And it's not the first time glaciers will melt, and it's certainly not the last time. Keep that in mind, because a lot of what we're seeing, we have no control over. The part that we may have an impact on, we certainly can try to ameliorate or try to do something about, but we can't stop natural climate variability. We have to understand it does exist, though. We have to understand what its limits are. You have to understand how good or bad it's been in the past. To give you some other numbers, the last time there was no Antarctica with ice cover was 20 million years ago. Last time Greenland might have been ice-free, about 125,000 years ago. How many times has Greenland been ice-free in the last 200 million years? We don't know, maybe at least 4 or 5. But it's something that does happen. And we need to be cognizant of what the indicators are that it may be coming to a fruition. So we need to pay attention to a number of things, including the geologic past. Okay, some numbers. As I mentioned before, if all of Alaskan ice were to melt, global sea level would go up about a 1/20 of a meter. If all the temperate glaciers on Earth were to melt, global sea level would go up about a third of a meter. That would start having some impacts, especially at the tidal basin, where tidal basin's underwater a certain part of the year anyway. If you melt Greenland, global sea level couldn't go up 6 meters. And if you melt Antarctica, you're looking at 73 meters of sea level change. No one is predicting that the melting of Greenland and the melting of Antarctica, are going to take place in the short term. But as the article in Science and in the Time magazine indicate, we're finding out something different now than we knew 2 years ago, and that is that the rate of the outlet glaciers that are draining Greenland and the rate of the outlet glaciers that are draining the peninsula of Antarctica are accelerating. Possibly because of two things. One, the meltwater I mentioned, lubricating the bed. And two, the removal of the ice shelves, the floating ice shelves that you heard all about over the last 2 decades, the breakup of the Antarctic ice shelves. Those acted as brakes. They kept the ice behind it constrained. You take away the ice shelves and the unconfined glacier velocities increase. Well, what does that mean? Well, if you increase the glacier velocity, you're sucking ice out of the interior in order to keep that flow moving. So you're losing ice from higher elevations and drawing it into the lower elevations, where it either goes directly into the sea and melts in the ocean, causing global sea level rise, or it melts at an accelerated rate at the lower elevations because temperatures are warmer there. And so it's this combination of melting because of increased temperature, plus in the coastal environments, the increase in rates of flow, that are the major factors that influence the role of glacier ice transfer into the world ocean and sea level rise. Now, as I mentioned, we have a name for this. We talk about eustatic sea level change, for the change in global sea level. And when we're talking about the total melting of all ice on Earth, which hasn't happened perhaps for more than 25 million years, you're looking at a maximum of about 80 meters of change. What we were anticipating over the next couple of 100 years, up until this new information about Greenland, was perhaps sea level change of a third of a meter from melting of temperate glacier ice. When you start coupling loss of polar ice as well, you have another interesting and presently still minimally understood issue that needs a lot more attention. And I'm sure we'll start seeing a much greater focus over the next year. In fact, it's happening now. That's what resulted in the Science article on what the implications are of the Greenland and the Antarctic Peninsula loss of ice. So, having said that, we've got a context now to look at Alaska and see how Alaska changes. And what we're going to do is take a quick survey and look at the 14 geographic regions in Alaska that support glaciers. Most people who look at a map of Alaska think the glaciers should be up here in the north where it's coldest. The reality is, where are they? Well, they're along the Pacific Ocean where you've got the moisture. Moisture drives the system. And in this area up here, even though you've got the Arctic Ocean, most of the year the Arctic Ocean has been completely ice covered. And the temperatures have been low enough year-round that the amount of water transferred from the Arctic Ocean to the atmosphere, although significant, isn't enough to produce substantial precipitation and build glacier ice in the northern hemisphere. In fact, as you'll see when we talk about the Brooks Range, every single glacier in the Brooks Range is melting. And many of them, when you look at what we call the ELA, the equilibrium line altitude, that's the altitude where snow remains at the end of the melt season, that elevation is above the tops of the glaciers. So we lose the 100% of the previous year's snow plus a significant percentage of older ice. And that's not uncommon in many places in Alaska. So we're going to start in the Coast Mountains and work our way around Alaska quickly, because I want to spend some time enjoying the photo pairs in Glacier Bay. I just throw this in to show that there's all sorts of data that we're using, everything from historic descriptions going back to the 18th century, aerial photography in Alaska that is spanning 80 years now, satellite imagery, including declassified corona data that goes back to the 1960s, and meteorological data, as I pointed out, that covers the last 50 or so years. Start with the Coast Mountains. Most people who go to Alaska as tourists end up in Juneau, and they end up looking at the Mendenhall Glacier. It's the most visited glacier in Alaska. It's one here in the Coast Mountains. But in Alaska, in the Coast Mountains, about 99% of all the glaciers that descend below about a mile in elevation, about 1,500 meters, are melting, they're thinning, or they're retreating. A handful of glaciers in this area are advancing, and we'll talk about some of them in a minute. Total area about 7,000 square kilometers of ice in the Coast Mountains. This is the South Sawyer Glacier. It's a typical, what we would call tidewater glacier. It's where this transition from land to ocean takes place. In Alaska, there used to be hundreds of tidewater glaciers. Now it's less than 50. Most of them retreated out of their fjords onto land. So calving loss is less of a factor in Alaska, but melting in those lower regions are significant. But it's this area, this transition between ice and ocean, that is the most critical area we need to be focusing on for future studies of how glaciers are changing in Alaska. This is the Taku Glacier, which has been advancing for the last 110 years. It actually was a tidewater glacier through about the 1940s, but it had enough sediment that it was producing that it built a protective barrier in front of it. And so now calving, and this happens to many glaciers, calving has become reduced and their rates of advance have increased. This is the Norris Glacier, which used to be much larger about 100 years ago and has been in retreat for the last 80 or so years. The two of them side by side, one advancing and one retreating, are not unusual. You get differences in regional behavior of glaciers. And for the most part, it's a function of not what you see here, but what you see way up here in the areas of accumulation. Advancing glaciers typically have higher accumulation and larger accumulation areas. And what happens down here, the rate of melting increasing is being augmented by increased ice volume flowing through. Whereas a glacier like the Norris has a lower accumulation area and there's nothing coming back to reestablish the volumes being lost to melting. This is a glacier called the Hole in the Wall, which only has been in existence for the last 60 years. As the Taku thickened, it overrode this ridge. Prior to that, it was in this basin. It overrode this ridge, and a new arm of glacier ice made it down to sea level. This one has also built a protective barrier in front of it. But this is the profile of a healthy glacier. A bulbous terminus, a profile, convex profile, and there aren't many of these left in Alaska. Less than 24 advancing glaciers in all of Alaska. This is more typical. This is the Mendenhall Glacier. Mendenhall Glacier was off the picture in the early 1800s. Actually, let me go back. It was off the picture in the early 18th century. About 1750, it was out here. And you can barely make out a series of ridges in here. Each of these is a recessional moraine that represents a point in the retreat of the Mendenhall Glacier. Mendenhall Lake didn't exist prior to about 1940. And if you were standing here, the example that you heard from Bill, if you were standing here where the visitor center in 1940, you would have been under the ice. Since then, the glaciers retreated 4 kilometers, opened up this huge basin, and here now, we're not looking at melt as the biggest factor. It's something very much like what I described here, the drawdown. In fact, it's a new process I've described that I call disarticulation. And everybody's heard of calving. In fact, typically people went to Alaska to watch glaciers calve. And calving meant the ice falling from height into the ocean, big splash, lots of noise, small pieces of ice. In disarticulation, what happens is glaciers that are in basins like this one, and the basins are the result because the glacier is thinning, and there's a ridge at the end that traps the meltwater. This glacier has thinned to the point where it's not thick enough to maintain contact with its bottom, with the bed that it was on. So it's floating. And as it floats, it starts coming apart along old fracture zones. And in this picture, this is a part of the Bering Glacier that we'll talk about a little later. The width across this island is 1.5 kilometers. So some of these pieces of ice, and you can see several hundred pieces of ice separating simultaneously, Some of them are half a kilometer in maximum dimension. And that's because the glacier has thinned to the point where it's floating and comes apart along old planes of weakness. A little bit of tidal flux, a lot of structural weakness in the ice. Meltwater gets in and lubricates the fractures. That was one of the causes that was identified for the glacier, or for the failure of the ice shelves in Antarctica. We're seeing the same thing in temperate glaciers in Alaska. And just last summer, I identified more than 20 of them from a 2-day aerial survey that are rapidly retreating. One I'll show you a little bit later, called the Bear, has retreated 3 kilometers in the last 3 years. So, moving on to the St. Elias Mountains. St. Elias is one of the largest in terms of both elevation and size of glaciers in Alaska. There are a handful of glaciers that are currently advancing, and we'll take a look at a couple of them. But the biggest story there is Glacier Bay. Glacier Bay, this is a MODIS image. This is a 250-meter pixel size image taken by one of the NOAA satellites. And what you see here is Glacier Bay. What you see here is the Brady ice field. This is part of the Glacier Bay National Park. But when you look at Glacier Bay, the two things that strike me are blue and green. If you were back here 250 years ago, everything would have been white. The glacier that filled Glacier Bay was here in 1750. So we've seen more than 100 kilometers of glacier retreat. And this is what we'll look at and document at the latter part of this presentation. But I'll give you sort of a bit of a tease now, and we'll take a look at the changes in Glacier Bay. 1750 to 1850, about 40 kilometers of glacier retreat. We probably lost 1,000 cubic kilometers of ice during that 100-year time period. 1750 to 1850. We're not talking about 1950 to 2000. We're talking about a period of time 250 to 150 years ago. Glaciers in Alaska were melting long before concern about industrial revolution, long before big concern about greenhouse gas buildup. Glaciers in Alaska have been responding to post-little ice age climate, in some cases for 300 years. Same is true in many other parts of the Earth's surface. Make sure you understand that there's no question we have major concerns about the impact of humans on climate, but climate was already warming before, at least in terms of impacting temperate glaciers, long before increase in human population, increase in human activities. So, let's go back, 1750, 1850, 1890. We've lost 80 kilometers of ice, linear kilometers. And Glacier Bay is now becoming a series of separate fjords. 1937, 1964, 1985. By 1985, all of the major glaciers in the eastern part have retreated off this map. So I don't bother going any further. But that's what we're going to look at, is this rapid change in Glacier Bay over the last 250 years at the end of this presentation. Other glaciers. This is a glacier called the Yakutat Glacier. It's about, maybe 100 kilometers west of Glacier Bay. This past summer, I was flying over it, and I noticed that it's already coming apart distances of as much as 4 kilometers from the terminus. It has almost no relief. This entire thing is mimicking, to some extent, an Antarctic ice shelf, and it's always showing the same kind of failures and cracking that we saw the last 2 decades in the Ross Ice Shelf and some of the other large ice shelves in Antarctica, the Ronne Ice Shelf and so on. It's also spewing pieces from its margin, some of which are up to 1 kilometer in size. Less than 50 miles, less than 80 kilometers to the west, on the other hand, is the Hubbard Glacier. Hubbard Glacier has been advancing for the last 130 years, and twice in the last 20 years has blocked this fjord, called Russell Fjord, caused water to build up in here to a point where it rose 25 meters in terms of water level in here. The catastrophic outburst flood that took place in 1986, and I can't give it geometrically, the number I have is 4 million cubic feet per second, about 2.5 times the largest Mississippi River flood ever recorded. And the flood that took place here in 2002, the last time it blocked Russell Fjord, was 1.8 million cubic feet per second. This glacier advances about 3 to 4 meters a day, but there's such a tremendous tidal flux through here that about 105% of the ice that's moving forward typically gets removed in summer and spring. And it holds its own by its rapid flow. But as it builds sediment in front of it, which I mentioned to you before is the protective factor that causes many of these tidewater glaciers to cease losing ice by calving, as it continues to build its next sediment protective moraine, it will again close this off. The two times it closed it, 1986 and 2002, it was a push of, it was what we call a push moraine, sediment being pushed up from the floor of the fjord that was effective in protecting and damming this. Eventually, when the ice gets here, and it will be there sometime in the next 50 years, it's going to make a major dam. And when that happens, this will flood through an alternative route into the Pacific Ocean, destroying one of the best salmon fisheries in all of Alaska. This is the largest Piedmont lobe glacier in Alaska, the Malaspina. It's immediately to the east of the Hubbard. And this mass, which is larger than the state of Rhode Island, has been thinning on the order of 2 meters a year, at least for the last 100 years. So we've lost 200 meters of glacier ice thickness over an area of about 3,500 square kilometers. Huge volume of water entering the oceans. However, there's still places here where there's 500 meters of ice. So at the rate of melting, we've got expectations this will be here a significant period of time, but definitely seeing dramatic changes. This is the next area to the west, Icy Bay. Icy Bay didn't exist. Like Glacier Bay, it didn't exist. Whereas Glacier Bay started to form in the 1750s, Icy Bay started to form in 1905. And since 1905, this is only the upper end of the bay, there's been about 50 kilometers of retreat. And this particular glacier, which is called the Tyndall, sitting up here, was here in the 1930s. A colleague of mine climbed Mount St. Elias just off this map in 1944. And at that point, the ice thickness here was 700 meters. And so there's been almost 20 kilometers of retreat and more than 2 kilometers of ice thinning just in the last 55 years. This is more typical of what you see when you get away from the coastline. Here's an old set of moraines. This is the glacier ice here. I don't know if the color stands out. This is blue ice, white snow. This is a picture I took in August of 2002 of an unnamed glacier in the St. Elias range. But this bare surface here is where the terminus of the ice was 1951. Here's where it was in the 1740s. So continuous thinning and retreat. And every glacier in the interior of the St. Elias range is melting and downwasting in this fashion. Chugach Mountain, some really interesting, unusual situations here, and we'll look at a couple of them. The Bering Glacier, this is the one I've spent most of my career focusing on. Largest glacier in North America. At the beginning of the 20th century, this black area here is a lake. At the beginning of the 20th century, it was solid ice that went from here all the way around like this. During the 20th century, more than 150 square kilometers of lake are formed by the melting, thinning, and retreat of the glacier. But this is an unusual glacier because it does something called surging, which means periodically it has a rapid advance in velocity, and parts of the terminus will advance up to 10 kilometers. And at various times during the 20th century, at least 4 separate times, most of this lake has been filled by ice that moved from a reservoir off the top of the image through the glacier at velocities of more than 100 meters a day and filled the lake. And the last time this happened was in 1996. Since then, here's a photo. This first photo, I'm sorry, this is before. This is 1990, before the surge. Here's the 2001 Landsat image. When you compare the two, you'll notice the lake is only about, it's a third smaller than it was because of the ice having filled it. Now in 2006, it's almost the same size it was again in 1990. So compare, look at the length of this peninsula of land versus, it's hard to see here, but it's only half exposed in the 2001 image. But you're looking at areas here where we get 1 kilometer per year on average of glacier retreat following each of these surges. And this is what the terminus of it looks like now. See all these dotted lines? It's literally falling apart through disarticulation along pre-existing fracture lines. So this is a 2002 photograph of part of the terminus. Here we are in the interior of the Chugach Mountains, and there are a number of telltale signs that tell glacial geologists what the ice has been doing recently. Notice this change from vegetation to bare sediment. That's what we call a trim line. And we can date this vegetation from photography. In fact, 1948, the ice was in contact with it. So here in the interior, about 100 kilometers inland from the coastline, the ice is thinned by more than 100 meters in the last 50 years. And also what you see, this is typical throughout Alaska. You see what had been small tributary glaciers that had been contributing to much larger valley glaciers, and now they are just small masses of snow left in the heads of their cirques, and they no longer make contact with the main valley glaciers. But not only that, when you look at the sides of the valley glaciers, you see these vertical planes the tops of which are the trim line, that represent the recent downwasting in the last 50 years, in this case of the Bering. Another interesting thing, this happened last September. Huge landslide came off of Mount Stellar, the highest peak behind Bering Glacier. This is what the toe of it looked like. I was fortunate to get a photograph that was taken the day after, and the picture looked like this. Here we are at 3,300 meters. Here's the summit. First thing caught my eye was this dark circle. That's a stream channel. In the side of this is a 30-meter thickness of ice from here to here. This had been a hanging glacier that had come down like this. The whole thing fell 2,500 meters vertically onto the back end of the Bering Glacier. Total volume, 50 million cubic meters of rock and ice fell. Created a magnitude 3.9 earthquake that was picked up around the world. That's how people knew there had been a landslide. Someone went out and took pictures. But this shows that there had been meltwater. There had been a stream flowing just below the summit of this mountain. It's hard for me to comprehend where that volume of water could have come from. But there's no question, and we have other photos that show the channel continuing. On this side, there was a stream that went like this through the head of this mountain. And it apparently lubricated the 60-degree slope hanging glacier, and it failed in September. And we have photos in in late October, early November, showing there's still water dripping down the face of that mountain. Hard to comprehend because I would have thought this would have been well below the freezing point by the beginning of September. But climate change is not only impacting the lower elevations, it's beginning to impact higher elevations in the coastal environment as well. This part of Alaska has probably seen a 2 to 3 degree C increase in temperature over the last 5 decades, with most of that warming being focused on the winter. Here's another interesting glacier. This is the Tana Glacier. In 1950, the ice, here's your trim line again, the ice came down like this. This is now the terminus of the glacier. Here's vegetation growing on the terminus. You can see some ice here that's falling off the wall. But this is a glacier that is melting away in place, it's stagnating, and as it melts, the sediment becomes a source for trees and shrubs to become established, and they come in very, very rapidly. And when we start looking at Glacier Bay, I hope you're amazed, as I am, at how quickly mature forests become established on what had been bare bedrock less than 100 years before. And we'll see that all over southern Alaska. But here's a good example of an unusual end member in rapid glacier melting and stagnation. College Fjord, and a little story here. The Harriman expedition in 1899 came up here, and most of the scientists were from Ivy League schools. So this was named Yale Glacier, this is Harvard. The Seven Sisters are the main tributaries on the west wall. And Harvard has been advancing for the better part of the last 80 years. Yale's been in retreat for half a century, side by side. Okay, Yale and Harvard. Smith has been advancing, it's stable now. Bryn Mawr has been rapidly retreating, but Radcliffe is one of the reasons that Harvard's advancing, because Radcliffe is actually makes up the entire western half of the terminus of Harvard Glacier. Okay, so interesting social dynamics in here. So here's Yale, and the picture is taken from the location where the glacier was in 1909. So you're looking at 6 kilometers of retreat, but not only is it retreating because of calving, it's thinning on its margins because of both drawdown and melting. Here's what Harvard looked like in 1909. The same day that picture of Yale was taken from that other spot, this is what Harvard looked like, and here's Radcliffe coming in. And you can see this is the width of Radcliffe. This moraine here marks the Radcliffe side of Harvard and the non-Radcliffe side of Harvard. And here's the same location, same photograph. Notice this mountain peak. Notice these peaks in the background. Same mountain peaks in the background. Harvard, the entire glacier has advanced to the point where the Radcliffe part is well off the plane of the photograph, but Harvard is thickened by almost 100 meters and advanced 1.5 kilometers since 1909, before and after. And you'll see a lot of these before and after pairs. I find it's a great way of conveying not only glacier change, but no vegetation, and we'll see that as well later. Same thing here. This is the next fjord over. Harvard and Yale are over here. This is called Harriman Fjord. This is Barry Arm. I put this in here because I want to show you a pair of photos that I took. The old one's 1909. The 2000 photograph of Toboggan Glacier gives you another good idea of not only how climate is changing now, but gives you some idea of insights prior to 1909. This is a 1909 photograph of Toboggan. Notice the trim line here. I showed you modern trim lines. Well, it seems that by 1909, Toboggan had thinned and lost about half of its maximum thickness. And from some of the dendrochronology that we've done, we and others have done, Turns out that this was probably about 1840 when it was at its thickest. Same location now. Notice this peak. Notice this tributary no longer makes contact. And in fact, all you can see of the glacier, there's a small amount of ice here. But notice the abundant vegetation that's come in. I mean, it's almost instantaneous. You don't go through centuries of forest succession. The seeds blow in from adjacent areas. The glacial till, if there is any, serves as the footing for them to get established. And within a decade, you got multiple species growing very, very rapidly. But what was most surprising to me, there are places where there's no till, it's just bare bedrock, maybe some cracks in the bedding planes. The seeds blow in, and before long, they're established. And you'll see some really interesting examples of that in a minute. Okay, so that's Toboggan Glacier. Move to the Kenai Mountains. Same thing there. Almost all of these fjords were filled with ice in the late 1800s. The glaciers have retreated anywhere from a few kilometers to 20 kilometers during the 20th century. And some of them, like Excelsior, are starting to thin and shed huge pieces of ice by disarticulation. This one's about 600 meters in maximum dimension. Now, this is Bear Glacier. This is a picture that was taken in 1909. Just watch it evolve. That's August 5th of last year. The glacier, as you'll see in an astro image I'll put up in a minute, has retreated about 7 kilometers, but the entire landscape has changed dramatically from just bare sediment plain to mature Sitka spruce and hemlock. This is where that photo was taken. The star marks that photo. And the glacier terminus at 1909 was along this line of white stars. Here's the large lake basin that's formed over the last century, but this is a 2001 astro image. Notice the terminus of the glacier here. This is a long finger of ice, extended to within a kilometer of the 1909 position. And also notice these two little pluses in here, because those are going to become very important. The distance from here to here is more than 3 kilometers. Okay, so here we are on June 9th, 2001. Here we are September 2002. Notice the pluses. Remember the finger of ice that was down here? It's gone. Look at this now. Here we are August of last year. There's the 2 pluses. We've lost about 4 square kilometers of glacier ice with a length of more than 3 kilometers through this disarticulation. Look at the size of some of these pieces of ice. But that's what's happening. We're seeing more and more glaciers now transitioning from melting to falling apart, to disarticulating. And even though this is an insignificant amount of water compared to what comes out of the polar regions, it is a dramatic change in the volume of water caught up in Alaskan glaciers. Yeah, I don't even put in the 2001. Here's the 2002, 2005. Another interesting glacier. This is McCarty, which was already in retreat in 1909. Same location in 2004. The glacier is actually about 20 kilometers off to the right, up its fjord, before and after. Now, one of my colleagues at the National Park Service took 2 photos, one from 1909 and one that he and I took last summer, and did this. And here's the change over a 90, what is that? We're looking at 86-year time, 86-year time period with loss of glacier ice and separation into just rapidly retreating, thinning former tributaries. Another example, same thing. This is 1909. This is the terminus of Northwestern Glacier. That's the current landscape. Whoops, come on, move forward. Okay, so that was the Kenai Mountains. That was this area here. Alaska Range, photo Stephen Capps took in 1919. One of my Park Service colleagues, Ron Carpillo, was back there 2 summers ago, same location. Notice the height of the ice, 1919. Notice a trim line. Here, in the center of Alaska, in the Alaska Range, there was already melting taking place. The glacier was already in retreat. Even though it had a significant debris cover that reduced the rate of melting, it's since retreated much more significantly. There's about an 80-meter thinning that's taken place over that 1919 to 2004 time period. And also notice the abundant vegetation that's moved in here, before and after. Talkeetna Mountains, just one photo to give you an example of the change. Glacier sat here in 1950. It's retreated about 3 kilometers between 1950, and that's a picture I took in 2000. In 2000, it was a flat gradient glacier. You could walk up it as if you were walking on a highway. It had separated from its tributaries and continued to retreat. About a third of the glaciers in the Talkeetna Mountains, and the Talkeetnas are the next mountain range north of the Chugach Mountains. About a third of the smaller glaciers in the Talkeetnas disappeared between the middle 1950s and the beginning of the 21st century. Wood River Mountains, an interesting glacier. There was a major project during the International Geophysical Year to visit 8 glaciers in Alaska and to do detailed topography of them. This is one of them, the Chickiminick Glacier. So this is a 1957 Navy photo. At that time, the glacier was down here. Of all the 8, this is the most rapidly retreating. It retreats about 15 meters a year. And so it's been thinning and down-wasting down here. One of my colleagues at the University of Alaska did laser altimetry studies, not only across the lower reaches, but went up both of the major tributaries. And what he discovered, it's thickening up here. And the total volume of ice in this glacier in 2001, I believe was the year he did it, was greater than he calculated for 1957. But it's a complete redistribution of mass. More accumulation in the upper reaches and a continuous loss in the lower reaches. And so one of the things I'll generalize about is at higher elevations in Alaska, we're not seeing significant glacier ice loss. We actually may be seeing thickening in places. But in most lower elevations, unless you have a glacier that's fed by a substantial accumulation of upper elevation ice, what we see is rapid glacier loss. Gigwalik Mountains, an area around Seward, Alaska, there were about 10 glaciers that were identified and mapped first decade of the 20th century. By the 1950s, only 3 of them were left. One of my colleagues from Northern Arizona University was back there probably a decade and a half ago, and at that point the 3 were there, but they were all rapidly disappearing. And the one that he focused on, the Grand Union Glacier, which had been here at the beginning of the 20th century, was just stuck under the head of its Cirque Valley with a little bit of ice up here, but the main part of the glacier here. But you can see all of this abandoned sediment that represented the moraines that the ice was in contact with in the last 100 years. Brooks Range, I gave you a statement before that every glacier in the Brooks Range is retreating and many have disappeared. I'll give you some photographic evidence of that. Leffingwell was one of the first geologists to go up to the Arctic and mapped more than 90 years ago, in fact about 95 years ago, photographed the Ukpillik Glacier in 1910. Matt Nolan at the University of Alaska took this picture in the summer of 2004. Again, thinning of about 100 meters. You can see that even in 1910, the glacier extended out of this basin and then down off the picture. But as this glacier retreated, probably somewhere around the 70s or 80s, it retreated back, exposed this lip, then was fronted by a lake, and the rate of retreat probably accelerated because it began calving and disarticulating into this lake through the latter part of the 20th century. In the Aleutian Range, we have some interesting anomalies. All the large glaciers in the Aleutian Range, and this is the Glacier Fork Glacier, all of them have been retreating. In fact, probably during the Little Ice Age, the Glacier Fork Glacier was way down here. But a number of these smaller glaciers, based on a Landsat analysis by some colleagues at USGS in Anchorage, about a third of these are currently advancing. Why? We don't know. But it was an interesting observation that just came out. They didn't have any explanations. They just observed that about a third of them are now advancing, but in the 1950s, more than half of them were. So the number that is advancing is decreasing, although they're still advancing smaller glaciers. But the larger ones are all retreating. Wrangell Mountains, interesting. There's one glacier on the flank of Mount Wrangell that's been advancing for at least since 1964. The 64 earthquake changed the entire thermodynamics of the Mount Wrangell area. And in fact, there's been about 200 meters of melting ice in the crater. The crater has a temperature of minus 20 year-round. And the thickness of ice in the crater has decreased by 200 meters because of increase, almost an order of magnitude increase in geothermal heat flow. And this one glacier called the Athna Glacier, which comes off of one side of Mount Wrangell, behaves as if it were a surging glacier. Its bed is continuously being lubricated by meltwater from the higher geothermal values that underlie it. And it is advancing even though it's not being nourished, so it's getting thinner as it's being drawn out, whereas all the other glaciers that come off the flank of Mount Wrangell are retreating. In the Alexander Archipelago, these are the small islands, southeastern Alaska, every glacier is retreating. And on Kodiak Island, where there are about 50 glaciers, every single glacier is retreating. Aleutians, we don't know that much about. We know that where we have good maps, the glaciers are disappearing. However, and I should have mentioned this before, there are two interesting sort of anomalies, but they make sense when you put them in the context. In 1912, Katmai erupted. Katmai was one of the most impressive eruptions during the 20th century. It completely destroyed all the glaciers in its summit. In fact, there are a number of glaciers on the periphery of Katmai, now in Katmai National Park, that are covered by enough volcanic ash that they haven't melted in the last 94 years. In the crater, though, it was ice-free after the eruption. And since then, at least 4 glaciers have formed in the crater, descending into the crater. So there's enough moisture and it's cold enough there that under the right conditions, moisture and temperature, you can still form glacier ice even close to the ocean in Alaska. The other example is Mount Redoubt. Redoubt erupted in 1989 and again melted the entire snow and ice content of its crater. It's completely filled with snow and ice again. Redoubt's at an elevation of about 28, almost 3,000 meters. So at higher elevations, above 1,500 meters in right moisture environments, we are still accumulating ice and snow in parts of Alaska. So, quick conclusions, and then we'll move on to Glacier Bay. Every Alaskan mountain range, island group, characterized by significant glacier retreat and thinning. All but a few glaciers, and there are probably about 20 in Alaska that are currently advancing. In many locations, glaciers have completely disappeared during the 20th century and early 21st century. Some areas retreat started 250 years ago or more. Some areas, and I didn't mention this, but in some areas we actually have more glaciers than we did a decade ago or a century ago, because as some of these larger glaciers retreat, they separate into individual glaciers. So we have a larger number, but a smaller area and volume. Not significant change at higher elevations. I didn't mention the number, but there are about 650 named glaciers in Alaska of about 50,000. And of the 650 named glaciers, there are only about a dozen that are currently advancing. Now, let's move on to Glacier Bay, and let's have some fun for about 10 minutes, and then I'll have used up my hour. This is a map of Glacier Bay National Park. I showed you what the bay looked like in the 1750s at the end of the Little Ice Age. You can see where the ice is now. It's retreated more than 100 kilometers in places. And this is similar to that animated diagram, but I put glacier names on it. Grand Pacific Glacier was the glacier that filled all of Glacier Bay in the 1750s. By 1850, it began to separate. So Grand Pacific became the principal glacier filling the western part of the bay, and Muir Glacier, which actually didn't get its name until 1881, became the principal glacier that filled the eastern part of the bay. By 1890, Grand Pacific retreated from here all the way up to the head of its fjord, and during that period of time, Reed Glacier, Lamplugh Glacier, Johns Hopkins Glacier, Carroll Glacier, and Rondeau Glacier all separated from it. Each of these now have their own fjords in the west arm of Glacier Bay. And they each act independently now. Glacier Bay is very interesting because in the west arm, about 20% of the larger glaciers are currently advancing. The other 80% are rapidly retreating. In the east arm, which is a much more continental type of an environment, every single glacier is rapidly retreating. So A is Adams, the main Muir, Casement Glacier, Burroughs, Plateau. These all separated out during the 20th century, and some of them have retreated, continued to retreat almost to the point of non-existence. So by 1937, Muir Inlet had opened almost to the point where Muir Glacier retreats off the map. And by 1985, it's long gone, and we'll have to look at it in photographs to see what's happened to it. So that takes us up to here. This is the area that is off the map. The map went across like this. And so we're going to look at about a dozen locations, and you'll see a yellow star on the image beforehand to give you some idea where we are in Glacier Bay. So we're going to start way down here. This is an area that was ice-free probably by about 1830. And so when it was first visited in 1906, no glacier to be seen. There's some icebergs on the beach. The ice is somewhere off here in the haze and the fog. But what's interesting is that there's no vegetation to be seen. Lots of bare bedrock. This is a big piece of limestone. This is a boulder of granite, and it's been covered by weathering, so it's already black in color here. But what's interesting here, the only vegetation that's there are 6,000-year-old stumps. One of the things about Glacier Bay, it's got a very, very dramatic history. That's trees, forests in place, buried by sediment, sheared by advancing glaciers during the post-Pleistocene time period. So over the last 10,000 years, there have been at least 3 advances and retreats in Glacier Bay, all documented by spectacular in situ stump records that have been radiocarbon dated. So we know that the trees in Glacier Bay, the stumps in Glacier Bay, the ghost forest, this has been called by some people, actually span a period of time from about 8,000 plus radiocarbon years before present to 1,500 radiocarbon years before present. And we have chronologies and advance and retreats in different parts of the bay based on sequences of these trees. Having said that, okay, keep this rock in mind, because the next picture is going to be from the identical location that this one was taken, and what you see is very little. There's that, you can just make out the cubic boulder, but we're going to move about 15 yards to the right so you can have a better comparison. And so here's the boulder. Remember, here's one of these fossil stumps, maybe not one of the ones that was there in 1906, but you can see how dense the vegetation is coming. Here's the storm high tide line. So vegetation expands right down to the high tide line. I didn't mention anything about isostatic. I mentioned eustatic sea level rise. I didn't say anything about isostatic change. Isostatic change has to do with when you load the crust, it deforms, you unload it, it rebounds. All the ice that was on the crust here at Glacier Bay probably depressed the crust as much as 50 meters. Once the ice disappeared, this land surface has been rising, independent of the regional tectonics. It's been rising because of isostatic readjustment. And here, it's come up about 10 centimeters, it's about 3 centimeters a year. So in the almost 100 years since that photo was taken, it's come up 3 meters. And so even though even though the land surface is coming up, the vegetation keeps on encroaching right down to the limits of salt water because it moves in so rapidly. So these are the before and afters, 1906 and 2004. We're going to move over here and take a look at Reed Glacier. This is an 1899 photograph by Grove Carl Gilbert during the Harriman expedition. The ice face here was probably about 30 meters high. It's June and there's snow cover, so you can't tell much about what the vegetation looks like. But when you see the next picture, you'll know that there certainly were no trees there compared to what it looked like 2 years ago. Same location. You can see cottonwoods in yellow. You can see this is a willow tree, Alaska cotton in here, and some alders. But this arc of sediment is the moraine the glacier sat on in 1899. And so the ice is now off the edge of the photo, and the vegetation is coming quite abundantly. Here's the before and the after. And to put that in perspective, here's an aerial. This is where the glacier was in 1899. Here's where it is now, almost 2.5 kilometers up its fjord. I won't take the time to go into the map, but we have a number of intermediate positions. And as you'll see when we move to Johns Hopkins Glacier, we've used that to build a little bit of a story about how the glaciers changed during the 20th century. So we're going to move over here to Johns Hopkins Glacier. And here's a map of Johns Hopkins Glacier. Here's where it was in 1929. Here's where it is in 2003. This is a glacier that's been advancing for most of the 20th century. And so where you're sitting, that may look like a mass of colors and may be difficult to understand, but each of these is a timeline with a date on it, 1945, 1961, 1988, 1998. Let's take a different approach and let's look at it differently. This is where Johns Hopkins was in 1929. 36, 41, 45, 48, 50. Retreated a little bit in the 50s. Some of these glaciers fluctuate. When we talk about an advancing or retreating glacier, we're talking about what it's doing now, but it may have done something different a year or two ago. 61, it was continuing to retreat into the early 60s. By 64, it was re-advancing. 70, 98, retreated between 98 and 99, advanced again to 2003. And this year, it's back here a little bit. This is Gilman Glacier. Johns Hopkins and Gilman have separated. So that's one way that we're trying to explain not only long-term glacier change, but short-term variability to get you to understand these are dynamic landscape features that respond to climate, respond to precipitation, respond to even small changes in annual differences. We're going to move up here into Tar Inlet, and this is where the Grand Pacific Glacier is now located. Interesting story about it. Here's the Canadian border. Grand Pacific retreated into Canada after the 1920s time period and remained in Canada until about 1970, at which point it crossed the border back into the US. Recombined with Marjorie Glacier. Since then, it's been separating and retreating back into Canada again. What's interesting, we have an agreement with the Canadian Navy, and they come in here and do maneuvers in front of what was formerly their passage into their homeland. And they were out there last summer. They had 3 cutters. But this is a glacier that will, I predict, retreat back into Canada within the next several decades. So here's the Canadian border. Here's the terminus of what is called Grand Pacific Glacier, but in reality, this dark mass of ice that comes out of this valley here is the Ferris Glacier, which used to be a tributary to the Grand Pacific. The Grand Pacific is back here. It's 100 meters lower than the Ferris, and the Grand Pacific doesn't even reach its terminus anymore. Show you another example of that. Here's a photo. This is Ferris in 1936. This is the Grand Pacific. You can see it's about 80% of the width of its terminus. This is Marjorie. Here's the Ferris, completely covering, this debris-covered dirty glacier, completely covering the width of the fjord, and the Marjorie. Let's move over here into Queen Inlet, and this is, I've got 3 or 4 photo pairs that are among my favorites in Glacier Bay. This area is by far the most interesting and the most dramatic, with the exception of one picture I'll show you in Muir Inlet. This is a photo from what's called Triangle Island in 1906. Bare bedrock, no vegetation, a tidewater calving glacier, the Carroll, that's about 3 kilometers across, and water depths here of 125 meters, based on NOAA soundings, in 1920. Same area in 2003. Notice willow, shrubs, anything, abundant vegetation. The glacier terminus is now a mass of debris. This area, this is a stream now that's coming out of here, but more than 130 meters of sediment fill in the last 80 years, before and after. Okay? Now, if you don't believe me, we'll go up the side of the valley here. A picture taken the next day in 1906 by C.W. Wright, the same photographer. Okay, and here we are looking, this is the deep fjord. Here's the terminus of the glacier. A little bit of shrubs in here, but mostly bare bedrock, but certainly no large trees. This is August of 1906, June of 2004. Notice this total mass of sediment covering the entire, what had been open inlet. You can see a good citrus spruce here. These are all alders, but the vegetation is coming in very, very rapidly. Now let's put it in perspective. There's the before and the after, but let's get it in the air and see how this has changed. Here's Triangle Island, this little dark mass over here. So that first photo was looking at what was a vertical tidewater calving terminus of a glacier here. That second photo was taken from up the side valley, looking this way. So you can see this huge mass of sediment, probably 2 cubic kilometers of mud, have filled this during the latter part of the 20th century. And the entire lower part of the glacier is covered by large amounts of debris-covered ice. This is the only bare ice that you can see in the photo. Let's move over here to East Arm, and let's go back into the 1890s. And this is what it looked like at the entrance to East Arm when Gilbert took this photo in 1899. And let's do a slow dissolve and look at this thing disappear. There's what's left of the Muir Glacier. This is actually a tributary called the Riggs. We'll go back if you want to see that one more time. And this is a distance of about 30 kilometers. So we're over here now. We had just looked at the mouth of Muir Inlet. We'll take a look at Wachusett, and we'll finish up with 3 photos in the upper part of Muir Inlet. 1961, Bill Field, who spent 60 years of his career documenting glacier change in southeastern Alaska, took this photo. And this is Plateau Glacier, which filled what's now called Wachusett Inlet, sitting here. Again, no vegetation, individual cobbles, probably a thin layer of glacial silt and sand. Same location, 2003. Let me go back, because notice the 2 people standing here? There are 2 people standing there, okay. Okay. We couldn't get them up there. The vegetation was so dense. So if you look really hard, there are 2 orange float suits over here on the side of the cliff here. But if you remember, the ice was right across here and down here. And there was certainly no vegetation, but look at the dramatic change there. Okay, Muir Glacier. I showed you disappear through the 1930s. Here's where it was in 1940. We're going to look at a photograph taken in 1941 from this location. Between 1940 and 1960, retreated about 6 kilometers. 60 and 80, about 8 kilometers. And 1980 to 2000, it retreated out of the water onto land and is continuing to waste away up here well above the fjord head in Muir Inlet. So we're going to go over here at White Thunder Ridge. And this is a picture. This is the picture that was on the flyer. Photograph taken by Bill Field in 1941. The thickness of ice here from here down to the bottom of the fjord is about 800 meters. The ice was up here in 1941. Let's go back. I don't even see any soil. I see some rocks. I see lots of foliations and bedding planes. I have no idea how all that vegetation is rooted. I mean, somehow it's stuck into something, but it's there. And it's not just scraggly little trees. I mean, you got big cottonwoods, you got willows, you got alder, and there are even some spruce coming in. But I mean, dramatic change in a 60-year time period. You've gone from totally virgin soil to mature forest. The interesting thing, and I'll take 10 seconds, 20 seconds to tell you, the description of Bill Field's 41 photo says, go up Wolf Creek drainage, come to a defile, go up the defile, and you're on the top of the bare bedrock. So it's a 15-minute walk. It took us 6 hours of beating through the bottoms of the alders, going by GPS, to find this location because there was no visibility. You had no idea what was up, which way was east or west. And if we didn't have the GPS, we would have never gotten there. We'd still be looking our way through the woods. So that's 1941, 2004. Okay, now we get to the realm where the older pictures are pictures I took. So I'm going back to places I went when I was a mere child, 1980. And this is McBride Glacier. Notice its height. Notice it's extending down to Muir Inlet. This is the shoreline of Muir Inlet. 2003. It's thinned by 150 meters. There actually is a fjord in here now that you can't see that's 1.5 kilometers long. Before and after. Now, this one's, let's put things in perspective. This is the ridge where the 1941 photograph was taken from. This is the Wolf Creek drainage that Bill Field said you go up this defile and you're there. We got lost somewhere around here. Okay, this is where Muir Glacier was, this is where Muir Glacier was, right across here in 1941. It is now over here. This is where McBride was in the 1980 photo I took. It's now back here. So now what we're going to do is we're going to work our way around the corner. And that picture was here. We're going to start looking over here now. This is a picture I took in 1976 when Muir Glacier had a vertical face that was probably 40 to 50 meters high and where people came from around the world to visit the Great Muir Glacier. It was still the dominant glacier in Glacier Bay National Park. And you can still see one of its tributaries coming off the mountainside and connecting to it. Also, there's enough water because of the calving, the big splash waves, that this lighter colored dike stays wet and algae can grow on it. It probably is also covered by the extreme high tides. So this is 1976. Here we are in 2003. No algae, no glacier, no terminus, no icebergs. Before and after. Dramatic change. And we're talking less than a lifetime now. One last pair, which is a little further around the corner. Okay, 1978. Again, we were kayaking that year on vacation, did our field work, and then went to spend time looking at the Great Muir Glacier. Took this and a number of other photos, but I'll be very honest with you, I didn't know there was a 4,000-foot high mountain, 1,200-meter high mountain sitting right there. Glaciers are really good at concealing things, but gives you some idea of, notice the height of the ice. I mean, we've lost about 85% of the total thickness of glacier. And this is 2003. It continues to retreat. It's on the verge of separating from its major tributary over here on the left-hand side. So to put everything in perspective for Upper Muir, the 1941 photo I showed you was taken way around the corner over here. That 1976 photo with the algae on it was taken from this outcrop over here, and this is the valley that the ice was coming over to connect to the terminus sitting here. The 1978 photo looking into the mountain was taken from about here looking this way. And here's the shoreline, and here's the Muir Glacier, which used to be the main reason people went to Alaska as tourists in the 1880s and 1890s. Now, a rapidly disappearing, rapidly thinning, stagnant mass of ice. And is Alaska baking? If you look at Muir Glacier, the answer is unequivocally yes. Is all of Alaska baking? Pretty much so, but we still have higher elevations getting a lot of precipitation. And that pretty much puts in perspective the story of climate change, glacier change, and the dynamics of Alaska over the last few hundred years. Thank you very much.
But those are awesome photographs and really an awesome story as well, and you tell it extremely well. Larry Lucas, a question?
Sir, I'll be happy to take questions.
Is there any indication during previous cycles like this of the rate of disappearance? 20,000 years ago?
No. No, all we can tell you is if you look at the maximum sea level lowering at the last glacial maximum and point of stability, it took 8,000 or so years for sea level to rise 110 meters maximum. What we're thinking is the worst case scenario now is significantly faster than that. Beyond that, we don't really have a good indicator. And in fact, the last period of geologic time when we had the temperatures we're anticipating getting was in the Pliocene. And that's 2 to 3.5 million years back, and we really don't have any way of doing decadal, even century, or possibly even millennial scale terrestrial determinations. We can do marine records and talk about variability in the marine environment, but we can't make a direct correlation to land.
You showed the temperature record going back to 1947. How good is the precipitation record? And this is for two reasons. One, the winter snow precipitation in the building up of the glaciers, but also the summer rain as a contributor toward melting.
Yeah. After World War II, the question, if you didn't hear it, is how good is the precipitation record during the same period of time that I showed you the temperature record? Give you an answer. First of all, in Juneau, just giving you an answer of what the extremes are, there's a temperature record that goes back to the 1870s. And it's discontinuous. It becomes pretty much continuous by 1885. And there's precipitation records that go with it. But somewhere around 1940, they moved the weather station 15 miles. So it's hard to correlate. All of the records that the temperature data are based on that I talked about are weather stations that have been set up by the National Weather Service following World War II using what is now still treated as first order instrumentation. So from what I read, the precipitation records are continuous and very good. Here are the drawbacks though. I didn't mention this didn't want to take the time. All of those, there are 21 stations that were used to compile that record. All of those are at elevations of above sea level, but most of them, I think 18 are below 500 meters, and only 3 of them are below 1,000 meters. So where most of the glaciers are coming out of mountains that are up to 6,000 meters high, there are no permanent weather stations above 1,000 meters. There are only 2 USGS-operated stations, one at the Golconda Glacier and one at the Wolverine Glacier, at elevations between 1,000 and 2,000 meters. And those have a 30-year record. So we have really reliable precipitation data for the last 60 or so years at lower elevations. We can't tell you much what's happening where the glaciers actually accumulate. And you can easily compare summer and winter. I've seen some studies in taking individual station data and doing detailed assessments of changes in precipitation. So yes, the data is good for that, but it doesn't really answer what we need to talk in big picture stories about glacier change. Yes?
Have these receding glaciers revealed archaeological sites that folks are really interested in?
The question is, are there archaeological sites coming up from below these glaciers? More so in British Columbia than Alaska. In Alaska, one of my colleagues at University of Colorado is actually funded by NSF to look at reindeer herding activities on the margin of one of the glaciers on the eastern side of the Wrangell Mountains. But most of these glaciers, because they are so dramatic, I mean, if you look at a typical 10 to 15 kilometer long Alaskan glacier, the total throughput from snow falling at the head making it to the terminus is less than 200 years because of the typical rates of velocity. Even in the biggest glaciers, we calculate that for Bering Glacier from head to toe, which is 140 kilometers, 200 kilometers, 140 miles, takes less than 400 years for material to move through. So it would only be if there were marginal archaeological sites that are covered and then uncovered. One of the other issues is there's just not enough people who have taken the time to look. I'm sure there'll be more because we know that at least 8,000 years of ice marginal hunting has taken place in Alaska. So I'm sure we'll find more, but the answer is very few up to date.
I know one question a lot of congressmen will ask is, but sir, is there anything we can do about this? And what is your reply when people ask that question? I mean, it almost seems like
my answer is, I don't
that.
say, yes, you can. No, I say, this is part of a much bigger issue. what we're looking at is just one of 5 or 6 issues that I would call their attention. Everything from pollution of almost all fresh water on Earth, loss of non-renewable resources, loss of renewable resources at rates that are not replenishable. And you can't just say, well, we're going to stop greenhouse gas emissions, because that's not going to fix the big picture. I would tell you, if I had to prioritize these things, my concern is water, far more than it is temperature change. We already have water wars, and as population may double over the next 50 years, there are going to be more than 2, maybe even 3 continents where water is going to be the major factor for major wars. And yeah, we should be really concerned about greenhouse gas emissions, but our economies and our lifestyles have evolved in a way that we can't fix unless we go to alternative energy sources we haven't even conceived of. So, you know, if everybody had a horse, put this in perspective, and instead of having 2 cars in your garage, you had a stallion and a mare, you know, we'd have other problems to deal with. That does, you know, I'm not trying to completely negate the situation with humor, but I mean, really, we need to be concerned, but there are a lot of things that we can do that we're not doing, but there are many things that there's no way that we're going to fix. We need to be much more concerned about the bigger picture. We certainly need to be concerned about things that are fixable. We need to start looking at ways of increasing automobile efficiency. We need to cut down on consumption of electricity. We need to do simple things that you don't require a graduate degree to figure out. And then we need to start looking for the new ways of coming up with a radically new energy. And it's hard, you know, we still have to rely to a much greater extent on the atom than we are. Certainly if we're going to have population doubling. But am I concerned? Yeah. Should a congressman be concerned? Certainly. The one thing that we need to keep in mind, you know, if these glaciers were sitting north of all the major cities in the northeastern United States, and the flooding and the other natural hazards that could come from the impact of changing climate, you'd have instant response. The fact that these glaciers are not anywhere where they have major impacts other than possibly Seattle or Portland makes this really low on people's screens. And if it's outside the limits of the U.S., nobody seems to pay much attention at all.
Tom Gentile.
Yeah, I've got 2 questions. One is just a rephrasing of Bill's question, or Bill's congressman's question, which is, are you willing to say or speculate anything as to whether these effects are or are not related to man-made sources, or just more part of the grander picture of climate change, which might be happening independent of us? The second question is, when you're talking about water sources, maybe I'm just a little confused, because for the most part, we don't rely upon glaciers for water. We rely upon, for the most part, rainfall and snowfall for water. And it seems to me the amount of available water we have, unless we make a concerted effort to now tap into glaciers for potable water, has more to do with changes in rainfall and snowfall than loss of glaciers.
Okay, let me take your second question first. It's a big we. One of the other projects I work on is the water availability in Pakistan and Afghanistan. There, at least 40% of the 40% of the water that flows into the river is going from east to west in eastern Afghanistan and Pakistan. It's coming from glacier and snow melt, with a lot of it coming from glaciers that are rapidly becoming smaller. Right now, they have an overabundance of water for hydroelectricity in places where they have dams because of the increase in glacier meltwater. 30 years from now, that may be totally different. There are several cities in the U.S., Boulder being one of them, that get their primary water supply from melting glaciers. Yes, the U.S. is not really dependent on glaciers. Most of agricultural irrigation water in central Canada, coming off the east side of the Rockies, is from glacier melt. And it's decreasing as the glaciers there have gotten significantly smaller. So it's not something that has a personal impact on us, but the hazard from glacier melting in Europe has been quite significant. There have been at least 4 or 5 major outburst floods from glaciers that have taken extensive numbers of lives. The last big one was at Kolka in Russia. I'm not sure exactly whether it was in Russia or one of the stands, but that killed about 200 people 3 years ago. Major, both flood, but the flood was triggered by a large glacier avalanche. A similar thing happened in Peru in the 1940s or 50s. It killed 40,000 people. So one thing we'll see is a definite increase in glacier-related flooding and catastrophic flooding, because it's not linear. A lot of this water is trapped in glaciers and is discharged catastrophically almost instantaneously. But yeah, we as a country are not really dependent on glaciers for a source of either potable water or irrigation water. Your other question, yes, I mean, there's no question that humans are impacting the system. The one thing that I can't answer for you is whether it's a 50%, a 60%, or a 5% impact. If you look at solar radiation and you look at sunspot cycles and you look at the long-term radiation trends, we should have been looking at more of a cooling trend that we were seeing pre-1975 continuing into the 80s and 90s in the beginning of the 21st century. But we didn't see it. We actually saw an increase in warming. And that may be directly as a result of the human activities. But it's one of these things that we just don't have a way of quantifying it. I mean, we can model it, but we can't point to it and say, that 3 degrees that we're seeing between 1970 and 2000, 88% of it is coming from increased greenhouse gas emissions. But in my mind, there's no question it is a definite factor and it's a significant one.
Corollary in that is that, I mean, given the rate of change, I could imagine that could be an argument that it's something that's happening on a more human time scale than geologic time scale. But I understood from a previous question that that's also not so obvious.
Well, remember what I told you between 1750 and 1850 in Glacier Bay? The amount of ice lost there, and it's not clear whether it was solely due to catastrophic calving or whether there was a significant melting component, we have no temperature data, was greater than the rate of loss currently. And so I don't want to say that without question the last 3 decades of the 20th century were the warmest ever, and it was because of human activity, because there are other events that we can definitely document that may well have taken place because of significant warming, local warmings, regional warmings, that we can't quantify. Ignoring that, if you only look at the last century, yeah, without question, the last 3 decades, much greater glacier retreat, much more extensive, and probably more a result of human activity than natural variability. But I can't put a number on it.
I think we'll make that the last question. I think the bottom line is it's getting harder for the tour operators, and if you haven't been there, run, do not walk, if you want to see the Muir Glacier. Thank you very much.
You're very welcome. Thank you.